Welcome back to Astronomy. We are in Chapter 12 on the small bodies of the solar system, asteroids, comets, and dwarf planets. And in this video, Part 3, we'll look at comets. Comets are known, and they have been known since ancient times, as these bright lights in the sky that have long tails to them. So we're going to look at why do comets have tails? Why do they grow tails? And here's a picture of a comet that has passed close to Earth. You'll notice as you look at the picture that there is this what's called the nucleus of the comet, the ball. I've described it as a dirty snowball, so a ball of ice. Now, when we say ice in the context of comets, it's not simply water ice. It could be other hydrogen compounds such as methane or ammonia, could be water also. But there's the nucleus. And coming forth from it is a tail. There's actually two tails. You can't really see two tails in this picture, but we'll talk about that. So the main part of a comet is called the nucleus. And again, think of it as a dirty snowball, which means a big ball of frozen hydrogen compounds, could be water, methane, or ammonia. So there's the snowball aspect. But a dirty snowball has debris, maybe rocks, specks of dirt in it. And so I want you to think of a comet that way. The nucleus of a comet has rocks and various minerals embedded in it. And it's the nucleus that is the source of material for the comet's tail. So if you look at this picture, the picture on the left, and notice the scale, 5,000 kilometers, that little line down below, and that is roughly 3,000 miles. That little line is about the distance across the United States from coast to coast. And this is what's known as Comet Wild 2. And then we zoom in on it. And this is a photograph taken from the Stardust spacecraft. And you can see that dirty snowball. Now, there was a July 4th spectacular one year, 2005. We launched a mission, NASA launched a mission called the Deep Impact Mission. It was actually named after the movie Deep Impact. They sent a spacecraft towards a comet, and the purpose was to come up behind Comet Tempel 1 and launch an impactor, a 370 kilogram impactor into it. The impactor, once it impacted the comet, the nucleus of the comet, was going to blow out a bunch of material, and the main spacecraft, the Deep Impact spacecraft, was going to capture the material and then return back to Earth. So that's what happened. And so here's a close-up of the comet when the impactor was crashing into it. So this was the first instance of being able to capture comet material and then bring it back to Earth for study. So a good, rare example of a sample return mission. Let's talk about the anatomy of a comet. There are four parts of a comet. You've already learned about the nucleus of the comet. That's the main, the ball of ice. And by the way, this picture is of Comet Hale-Bopp. And it says the inset shows the nucleus of Halley's Comet. All right, the other three parts of the comet. When a comet comes close to the sun, into the inner solar system, basically at about 5 astronomical units, so at about Jupiter's orbit, then there's going to start to be sublimation, which is the solid material of the comet is going to start to turn to gas as it heats up. And that gas around it is called a coma. Now, coma comes from the Latin word for hair, and so you can just imagine this ball of ice with some fuzzy cloud around it. So a coma is the atmosphere that comes from a comet's heated nucleus. Now, we often think of comets as having a tail, but actually there are two tails. One is a plasma tail. Now, the plasma tail in this picture is the blue that's going straight down and to the left. The plasma tail is gas escaping from the coma that's pushed by the solar wind. I say it's gas. Remember that plasma, sometimes considered the fourth state of matter, is ionized gas, and it's being pushed by the solar wind. There's a stream of particles always coming from the sun in all directions. That's what the solar wind is. So being pushed straight away from the sun. Now, the direction of the plasma tail is not behind the comet necessarily. Normally we think of tails, like animals' tails, as going straight behind the animal. It doesn't go behind the comet, but rather it always points away from the sun. No matter what direction the comet happens to be traveling, it points away from the sun. So you can imagine, as it shows up here, the sun is up here where my pointer is, and the solar wind is pushing that plasma tail straight back. Now, the other tail is the dust tail. Remember, I said think of a comet as a dirty snowball. So there's all this debris, these minerals, these rocks that are embedded in it. Well, as the material from the comet sublimates, it lets go of these rocks and minerals, and it gets pushed back by light. So light actually does produce, it exerts a bit of a pressure. And those photons, that light, pushes the dust backwards. But the thing is, the dust isn't having some mass to it. It doesn't get pushed backwards very well. It gets pushed back a little bit, and it leaves a trail that trails back. It kind of bends back in the direction that the comet came from. So it's often got this little bit of curve to it. So when we look at this picture, we can tell the direction that the comet is moving. As you can imagine, the dust tail sort of goes behind the comet. It mostly goes away from the sun, but then sweeps back in the direction the comet came from. So you look at these arrows at the upper right hand, we can tell by the direction of the plasma tail that the sun is in the opposite direction, so straight up that way, up and to the right. And we can tell the fact that the dust tail bends back towards the left, that the comet is moving to the right. Let's follow a short period comet as it goes around the sun. And let's start it up here at the upper left hand. Far from the sun, the nucleus is frozen. So there it's just a ball of ice. And remember that most comets are way out in the Oort cloud or way out in the Kuiper belt. And so most comets do not come close to the sun. This picture here that you're looking at is describing a very, very rare minority of comets that actually come in close enough to the sun to develop a tail. Although it's important to talk about because any comet that you'll read about in the news that you'll see maybe up in the sky with a telescope, those are these types of comets, these short period comets that come close to the sun. So far from the sun, the nucleus is frozen, and now it's coming closer. The nucleus warms, and ice begins to vaporize into gas. And remember, I've called that sublimation, where solid turns straight to gas. Then, as it gets to about Jupiter's orbit, which is 5 astronomical units from the sun, the coma begins to form. And actually, going back, I'd say the coma was beginning to form back here when the ice was starting to vaporize. But now it's more pronounced, it's more visible. It's a coma that we can actually see. So the coma has now formed around the nucleus. Still no tail yet. Now as it continues on in towards the sun, the tails form by about 1 astronomical unit, so about Earth's orbit, from the sun, and the tails point away from the sun, as I showed you in the previous screen. The plasma tail points, remember, away from the sun, and it's the solar wind pushing it away. Solar radiation, which is the light coming from the sun, pushes the dust tail out, and the dust tail, it gets pushed out, but then gets laid down in the direction where the comet came from. Then the comet continues around, and you can see in this picture, the pictures where the comet has the tail. Notice, I want to emphasize, the tail does not go behind the comet. The tail points away from the sun. Now, The larger particles are unaffected by sunlight or the solar wind. So these rocks and minerals, these flecks, this debris that's embedded in the comet, some of it is larger mass than others. And the larger ones, they're not going to get pushed by light. When you think of rocks that you find on the ground, they're too massive for light to push them. So they tend not to get pushed away at all, and they're just going to get laid down in a trail. Now, we're going to come across that trail later because that trail of rocks that's left behind is actually the source of meteor showers. We'll talk about that in a bit. The comet continues around the sun, and the tail gets shorter and shorter as it gets to colder areas of the solar system away from the sun. There's not as much sublimating. And then by the time it gets back to about Jupiter's orbit, it says here sometime between 3 and 5 astronomical units, the solar heating diminishes and the coma and tail disappear. So it is a nucleus. Once again, a nucleus by itself, and then the cycle will continue as it goes around the sun. This animation emphasizes the direction of the comet's tail, the plasma tail being the light blue, always pointing away from the sun, and the dust tail is going away from the sun, but then trailing a little behind the comet. Now, one way that this animation is inconsistent with what I just taught you in the previous screen, remember that if the comet goes far enough away from the sun, beyond about 5 astronomical units, beyond Jupiter's orbit, those tails are going to disappear. And so this animation actually represents a very short period comet that never goes beyond Jupiter's orbit. Another thing I want to point out, that where this is not truly realistic, this animation you're watching, is that, remember, as it gets closer to the sun, it goes faster, and as it gets farther, it goes slower. But the animator who made this didn't have that in mind. This is pretty neat, watching a comet become active. So this was from September 2014, the Rosetta mission that did some good close-up study of a comet named Comet 67P. And the first picture on the left, it shows before substantial comet activity had begun. So here it's just a nucleus, although you can see a little bit that stream coming up from the center. That's a little bit of sublimation going on. And then 2 months later, as it got closer to the sun, you see more sublimation. And then here is a jet shortly before perihelion. So the material seems to be coming from this one source on the comet. I want you to remember the main parts of a comet. The comet itself, the ball of ice, that's called the nucleus. And then there's a coma, the dust tail, and the plasma tail. And when it's far out beyond Jupiter's orbit, remember it's just the nucleus. The coma, followed by the tails, only develop when it gets close enough to the sun for that heating to occur. And here's a nice picture. The picture on the left is just a nucleus with a coma around it. And then this is a comet that's pretty close to the sun, and we can see the plasma tail is the blue going straight back from the sun, which tells me that in this picture the sun is up and to the left, and the dust tail coming kind of away from the sun, but then trailing back, so showing that the comet is probably moving up and to the right in this picture. I mentioned the trail of rocks that are left behind. Comets eject small particles that follow the comet around in its orbit and cause meteor showers when Earth crosses the comet's orbit. So whenever we encounter a meteor shower, and there are some meteor showers throughout the year, they are periodic, they are regular. We can count on the same day each year, meteor showers, certain times through the year. And this is when the Earth crashes through the trail of rocks that's been left behind. And in fact, for most meteor showers, we know exactly what the culprit was, what comet it was that left it behind. And the analogy is, it says, meteors in a meteor shower appear to emanate from the same area of the sky because of Earth's motion through space. And the analogy is driving through a rainstorm or snowstorm, and they appear to all be coming from the same direction. So we have meteor showers. We call them the Orionid meteor shower, the Perseid meteor shower. And that refers to, based on the motion of the Earth going through space during the Orionid meteor shower, all the meteors seem to radiate out from, they seem to all be coming from the Orion constellation. The Perseid meteor shower, they're all coming from the Perseus constellation. And that just means that the Earth is moving in that direction, crashing into all those rocks. And then we learned in an earlier video what meteors are. That is when those rocks enter Earth's atmosphere, they heat up from the friction, and we see those streaks of light. It's another beautiful picture of Comet Hale-Bopp with the plasma tail and the dust tail. Where do comets come from? I gave a brief introduction to this in the first part of chapter 12, and also back in chapter 7, looking at the layout of the solar system. Only a tiny number of comets actually enter the inner solar system. Most stay very far away from the sun. The ones that enter the inner solar system, we tend to call those the short period comets. They usually have short periods of orbit. Although occasionally a comet from very, very far away out in the Oort cloud will enter the inner solar system. It would be a very rare event, but a few years ago we had a comet that was visible in the sky, which means it had a tail. It was within Earth's orbit, and they calculated its trajectory and found that it had a period of something like 100,000 years. So it's one that came from way out in the Oort cloud, having a period that large. But generally, the inner solar system ones, those are short period comets. There is the Oort cloud. So the Oort cloud, remember, is a large, very large shell, spherical shell around the sun. And these comets have randomly inclined orbits, and it extends out to about 50,000 astronomical units. Now think how big that is. Neptune, the last planet, is 30 astronomical units. If you want to throw Pluto in there, Pluto is at 40 astronomical units. Now we're talking, these comets sometimes are out as far as 50,000 astronomical units. So that is about a quarter of a light year. Now, the Kuiper belt extends, in the graph that I pulled from the internet, it says here extends from about 30 to 50 astronomical units. And it goes beyond that. So there's some debate about how far it extends. I'm going to say 30 to 100 astronomical units, although it's kind of debatable how far it goes. But for purposes of this class, just learn that it's from 30 to 100 astronomical units. It's a disk, so it's kind of like the asteroid belt. It's all in a disk that orbits around the sun, but it's farther out than the asteroid belt. If it starts at 30 astronomical units, that means it starts at about Neptune's orbit. And in fact, Neptune's moon Triton, it is believed, once was a Kuiper belt object, so a comet that got captured by Neptune's gravity and turned into a moon, which explains its bizarre orbit. So it says here the Oort cloud contains about 1 trillion comets, and that is speculation. They haven't witnessed 1 trillion, but just doing statistical analysis of the comets that they can see, they estimate there might be about 1 trillion comets out there. So here we have in the picture, you've got the sun. This blue oval is Neptune's orbit, and starting from it is the Kuiper belt, and then much larger around it is the Oort cloud. And there's a zoom in on the Kuiper belt. We've got it starting at Neptune's orbit. This is a better picture of it. And then here's Pluto, which is a Kuiper belt object. And there's an image of the Oort cloud. So we have the Oort cloud, which is the comets that are way far away from the sun with randomly inclined orbits. We have the Kuiper belt, and then short period comets. These are the ones that we see coming in near the sun. And here we have one displaying conservation of angular momentum. As it comes closer to the sun, it goes faster, and it goes farther, it goes slower. A little history about comets. A comet moves slowly across our sky. Its movement is generally noticeable over days and weeks. So if you look up in the sky and you see a light streaking across, moving across the sky, if you can see its movement over the course of a few seconds or even a few minutes, it's not a comet. It could be a satellite, it could be an airplane. If it's moving very fast, it might be a meteor. But a comet is something that from hour to hour, it's going to stay pretty much in the same place. Its movement is noticeable over days and weeks. People have seen comets from ancient times as these things up in the sky. Comets were assumed to be in Earth's atmosphere until the year 1577, when Tycho Brahe used observations from different locations to show that a comet lay farther away than the moon. So he observed a comet from one location, observed it from the other location, and by observing, I mean measuring the angle that it is, its angle of altitude, and he was able to do some geometry and figure out that it is far away, farther away than they knew that the moon was. In the 1600s, Isaac Newton showed that comets orbit the sun. So remember, it was Kepler who came up with the laws of planetary motion in the early 1600s. In the late 1600s, Isaac Newton showed why the planets obey Kepler's laws of motion. And then he also showed that comets obey that as well. They orbit the sun. Probably the most famously known comet is Halley's Comet, and it's named after Sir Edmund Halley. In 1705, he used Newton's law of gravitation to calculate the orbit of this comet that had last been seen in 1682. So he didn't discover Halley's Comet. In fact, it had been known about. People had seen it since ancient times. But he took this comet that had come by in 1682, used Newton's math, and he calculated, and he said it has a period of about 75 years. And he predicted that it would return in 1758. And so it got named after him. That's Halley's Comet, the comet that Halley was writing about, that he predicted it would return. And it did return. Now, Halley had already passed away when it did return, but yet his prediction was correct. So it comes around every roughly 75 years. It returned most recently in 1986. And so it will return in 2061. Its period of 75.3 years means it has a semi-major axis of 17.8 astronomical units. Now, I want you to think back earlier in chapter 7, I asked you to memorize the distances of the planets from the sun, at least the planets beyond Earth, so that when I give you a number like 17.8 astronomical units, you have a feel for how big that is. So let's just review. Remember that Jupiter is 5 astronomical units from the sun. The next planet, Saturn, is 10. Uranus is 20. Neptune is 30. So its semi-major axis is 17.8 astronomical units. Now, actually, Halley's Comet, even though that's its semi-major axis, which is its average distance, it has such an elliptical orbit that it goes out a bit past Neptune. And so here is an animation of Halley's Comet. There it goes out past Neptune very, very slowly, and then speeds up as it comes in the year 2061. It'll speed up and whip around the sun. Here is the path of Halley's Comet, and we have It was approaching Earth in 1985. There they have this back to 1948. It was at aphelion, the farthest point from the sun. And then it got to Uranus's orbit in 1977 and Saturn's orbit in 1983 and Jupiter's orbit in 1985. And then it whipped around. So 1986, it was near Earth. And then it came back around 1987. Notice that it was at Jupiter's orbit. And then 2 years later, it had whipped around and come back to Jupiter's orbit again in the span of 2 years. But then notice how the years get lengthened. And so it goes out and it's going slower and slower and slower. And so 9 years later, in 1996, it's out at Uranus's orbit. Perihelion was in 1986. Aphelion is in the year 2024. So in 2024, Halley's Comet is at its farthest point from the sun at aphelion, and then it's going to turn in and make its journey towards us, and hopefully we can see that in the year 2061. I also want you to notice off topic, but notice this is well drawn, the orbit of Pluto. Notice the orbit of Pluto is so elliptical, it actually for 20 years, it comes inside Neptune's orbit. This is the ecliptic plane of the planet's orbits. And we have Pluto, which is off the ecliptic plane, but also notice Halley's Comet is as well. And down below is a picture of Halley's Comet. Of historical note, there is an association between the author Mark Twain and Halley's Comet. He wrote, "I came in with Halley's Comet in 1835. It is coming again next year, and I expect to go out with it." Mark Twain was born in 1835, and about 2 months after he was born, Halley's Comet was in the sky. And this quote references as it was 1910. Mark Twain passed away on April 21st, 1910, one day after Halley's return. So Halley's Comet was there when he was born, and it came around the sun and was back again when he passed away. And by the way, let me mention Mark Twain, totally off topic, but except talking about Mark Twain. As we study astronomy, sometimes we get into some weird topics, and one topic that we can get into is relativity, Einstein's relativity, and some possibilities of time travel. And Mark Twain wrote a book. As far as I know, it's the earliest science fiction story of time travel. It's the earliest that I can think of. It's called A Connecticut Yankee in King Arthur's Court. And so he wrote this. It's about a man from Connecticut who time travels. He just goes back. He wakes up in King Arthur's court. And so it's a really neat book, but I like it just because it is a good story, but it's a very, very early example of time travel in science fiction. So I recommend it. Another historically notable comet is Julius Caesar's comet. Julius Caesar, he was assassinated by the Senate in the year 44 BC. And in the Roman Empire, the Caesars were thought of as gods. They were thought of as deities. And so Julius Caesar, he was assassinated, he died, and within a few months, there was a comet in the sky. And many looked up at the comet and believed that it was the spirit of Julius Caesar going away from the earth. Several decades later, the emperor Augustus Caesar, who had also been Julius Caesar's nephew, he decided to hold some games, like Olympic games, that were in honor of Julius Caesar. And while these games were going on, The comet reappeared because remember these comets, it was a short period comet, so it reappeared. This comet was up in the sky. And people were fascinated and delighted because whereas decades ago, many remembered having seen the comet when Julius Caesar was killed, now they saw it returning and they thought this was Julius Caesar coming back to watch the games in his honor. The Roman Empire, they produced some coins that actually honored this comet and Julius Caesar. And so here it is. It says here on the front, Julius Caesar, and there's his image. And this in Latin, it says Divus Julius, the divine Julius. And this is supposed to be a comet right here, a picture of a comet. So as we think back over this video, what have we learned? Why do comets grow tails? Remember that comets are balls of ice, of hydrogen compounds. They are like dirty snowballs. So balls of ice with minerals and rocks embedded in them. Most comets are far from the sun and do not have tails. It's a very, very rare minority of comets that actually come in close enough to develop tails from the heating of the sun. The tails grow when the comet nears the sun and the nucleus heats up. First, it develops a coma, which is the atmosphere around it, the fuzzy atmosphere. And then as it gets closer, it develops the tails. Where do comets come from? Comets in the plane of the solar system, meaning in the plane of the planet's motion, come from the Kuiper belt. Comets that are on random orbits come from the Oort cloud. And that is it for our study of comets. Have a great day.